Alright, let's take a look at this third example. So you have a light plane that's traveling at 175 kilometers per hour on a heading of north, 8 degrees east of north. So let's draw that. When you draw these vector diagrams, make sure you draw them large enough so that you could label the angles and see them clearly. Now this plane is going at 8 degrees east of north. Here's north, here's 8 degrees east, and the other vector that we want is 40, which is about 1/4 the size of this vector. That's your plane vector. That's 175 kilometers per hour. And this angle in here is 8 degrees. Small angle in here. Okay, so just like the previous example, we could draw the set of the new origin at the head of our plane vector. So we could draw it like this. And from that we have a wind that's coming from 80 degrees east of north. So again, the same idea. There's north, 80 degrees would be like this. However, again, it's coming from, that's your key word here. And so your vector must be like this. Okay. So there's a wind vector coming in this direction, and it is about 1/4 the size of the other vector, approximately. There it is. There's your vector that's coming in. So we know that this angle is 80 degrees, this one over here. And we also know that this angle in here is 10 degrees. Okay, so this vector, we're going to have to move it so we join the tail of the wind vector to the head of the plane vector. So we're going to take this vector and draw it here so it looks like this. And that then enables us to draw the resultant. So this plane, again being affected by this wind, is going to push it this way so that the flight ends up going in this direction. So this is your resultant. And this is going to be the ground speed of the plane. Now we could do the same thing that we did last time and find this angle in here and use the cosine law as well. So let me just label everything we can on this diagram. This is 40 kilometers per hour, 175. This is your resultant. Make sure you label the vectors. And let's see what angles we have. We have this angle 8 degrees in here, so if you look at the Z pattern right over here, then this angle in here must also be 8 degrees. So same as the question before, you could take 90 degrees, subtract this angle in here, which is going to be 10 degrees because you have your opposite angles here. So this angle here, see how I'm going to label this. Let me do this. And I'm going to label this as 10 degrees, and that's because of your opposite angle, same as that one. And this would be the one that we're looking for, this one in here. So you could again take 90 degrees, subtract the 10 degrees, and subtract the 8 degrees to get this angle here, which is 72 degrees. Or another way of doing this is to picture this vector. So another way that you might come across of drawing this is to picture everything happening at the origin, at first origin. So let's say this vector, and it must be parallel, is over here. So you have the wind vector over here. That's your wind vector. And this wind vector is coming in at an 80-degree angle. So this angle over here is going to be 80 degrees from here to here. This is 80 degrees from here to here. So if this is 80 degrees, then 80 degrees, take away 8 degrees, this little sliver of an arrow here, gives you a 72-degree angle from here to here. And if that's 72 degrees, then you can think of your Z pattern, which would make this yellow one also 72 degrees. So that's another way of viewing it. Of course, if you were to draw your angle, your vector over here, you would still have to move it up here. So let's take a look at the calculations for the resultant. Again, the magnitude of r squared using cosine law is equal to 40 squared plus 175 squared minus 2 times 40 multiplied by 175, and then the cosine of this angle here, which we established was 72 degrees. So let me also write that down for you. So we also said that we could find it, two ways we could find it. The other way, using the same method that we used in the previous question, was to take 90 degrees, subtract this angle here, which is 10 degrees, and then subtract this angle here, which is 8 degrees, and that comes out to also 72 degrees. Okay, so let's finish this off. 40 squared is 1600 plus 30,625. Take away all of this, starting with cosine of 72 degrees, is 4326.2, and that comes out to be 27,898.76. Then the magnitude of r is equal to 167 kilometers per hour. Now we would again use the sine law in order to find the angle. And the angle that we're looking for is theta, right over here. This is the angle we're looking for. This big angle over here, theta. Okay. We have this side, that's 40. We could pair it up with this angle, and we have a known side, which is your resultant, which was 167, and paired up with this angle in here, which we know of as 72 degrees. So 167 over the sine of 72 degrees is equal to 40 over the sine of angle theta. Sine of theta comes out to be 0.227798, and angle theta comes out to be 13.2 degrees. So now we need to do a little subtraction. We need to subtract 8 degrees from that in order to get this angle here, and then we could say that the plane is flying at such and such ground velocity, so many degrees west of north. So 13.2 degrees, take away 8 degrees, comes out to be 5.2 degrees, and therefore the plane's ground velocity is 167 kilometers per hour, and it's going to be 5.2 degrees west of north. Now let's take a look at the next question, the last question for this lesson, and it deals with a swimmer who's swimming 3.5 meters per second in the pool, heads directly. We can swim 3.5 meters per second in the pool, but this guy is heading directly across the river that has a current of 2.0 meters per second. Calculate the swimmer's actual bearing and speed relative to the shore. Okay. So here's your river. Swimmer is heading directly across the river. So the swimmer is going like this. And the swimmer is going at 3.5 meters per second. So you have the current of the river that's flowing. It doesn't tell you which way it's flowing, so I'm going to assume that's flowing this way. And this current flows with the river, so it's going to be perpendicular to this one. And that vector is 2, so something like that. And this vector is 2.0 meters per second. So again, if you think about it, your swimmer is going like this, and the current is pushing the swimmer along, so the swimmer is going to be following a pathway that looks like this. So this is the resultant. R along here. And since this is 90 degrees, we could again use Pythagorean theorem, so that the magnitude of r squared is equal to 2.0 squared plus 3.5 squared. And that comes out to be 4 plus 12.25, which is equal to 16.25. So the magnitude of r comes out to be 3.50 meters per second. Okay, what we also need to find out is this angle in here, theta, and I'm going to call this theta 1. So to find this opposite adjacent, you're going to use the tan ratio. Tan of theta 1 is equal to opposite, which is 2, over your adjacent, which is 3.5. and angle theta 1 comes out to be 29.7 degrees. Now, in order to conclude, we're going to talk about the angle relative to shore. So the angle that we're actually interested in is this angle over here. So if you could picture this whole thing shifted down, I'm going to redraw the shore. I'm going to move the shore up a bit so you can see. Okay, there's water. So this is the angle that we want. This one here. Easy calculation, theta 2 is equal to 90 degrees, take away 29.7 degrees, which comes out to be 60.25 degrees. And we can conclude that, therefore, the swimmer's actual speed is 3.50 meters per second. The bearing relative to shore at a bearing of 60.3 degrees relative to the shore. So a quick reminder that when you're talking about angles, remember you're going in a counterclockwise direction. So if you picture this as being the positive x-axis, that's the shore, you have to go this way. Okay, so it's similar to what you encountered before relative to the horizontal. And that's it.